Welcome to this video. We are going to briefly see a couple of key facts about static friction. Let's say there's a block and it's really heavy and it's sitting on the ground. The block's center of mass is this dot right here. There are some forces acting on the block. Gravity pulls it down, and because of gravity, the block is pressing against the surface. Newton's third law says that the surface pushes back up on the block. Now you come along and you try to push on this block. And you don't push very hard. A small applied force. What happens? The block doesn't go anywhere. It remains in equilibrium. And what that means is another force has to balance out your rightward applied force. So there's another force pushing to the left. And that's static friction. Then you come and you push a little bit harder against the block with a larger applied force. What happens? The block doesn't go anywhere. It remains in equilibrium. That means there must be another force pointing to the left that's equally strong as your push. Again, that's static friction, and we could describe it as the grip or the traction that objects have when resting on surfaces. And one more time you come and you try and push, you push even harder, and you push with a bigger applied force, and what happens? The block still doesn't budge. So you are being opposed, your force is being opposed by some other force, which is static friction. We consider the three scenarios. Here they are. In each case, the downward arrow is the force of gravity. The upward arrow is the force of the floor supporting the block. We call that the normal force because it's normal to, or perpendicular to, the surface itself. And then there was this rightward arrow that grew. It represented the applied force. And finally, why didn't the block move when you pushed? Because there was this opposing force, and that was static friction, the force of static friction, which we think about as the grip or traction the block has. A few important things to note. In these scenarios where we're putting our hands on the block and pushing, the static friction always balances the applied force. Another way to think about that, if not for static friction, there would be an unbalanced applied force. So static friction is what places the block into equilibrium. The next thing to show is that when the applied force grows, as it grows, what happens to static friction? This force is small, then medium, then big. The static friction force grows too. Now here's the thing about static friction. It cannot grow forever. Eventually, it reaches its limit. It has a maximum value. Let's imagine that this right here is the strongest static friction can pull or push. Instead of calling it just Fs, we label that Fs max. Now what happens if you push stronger than static friction's maximum limit? If you push any harder, the block starts to slide, and then kinetic friction kicks in. So once you push harder than Fs max, static friction lets go, so to speak. So there are two separate equations we use for static friction. The first one applies to these scenarios where there's something pushing on the block, and it says the static friction force always matches or balances the applied force. That's because static friction is what puts the block into equilibrium. The second equation looks a lot like the kinetic friction equation. The maximum static friction force is equal to this value mu sub s, the coefficient of static friction, times the normal force on the block. So if you reduce the normal force, maybe by lifting up on the block, static friction cannot get as big when you do that. A few notes on the two equations. Here they are. That's the static friction equation, and here's the kinetic friction equation. We see they're nearly identical. These quantities tell us something about the roughness of the surfaces that are sliding across each other or that aren't sliding across each other. They also are fixed for any two given surfaces. If you want to look at concrete on tires or rubber, let's say, concrete and rubber have a fixed value of mu k and mu s. The last thing is that they don't have any units. If we ignore mu for just a second, the left side has units of newtons. The right side also has units of newtons. So mu cannot have any units, or else it would interfere with the equality of newtons equaling newtons.